see binary. Okay, let me see. Let me show you the slide. This is, as I mentioned again, this lecture will be covering specifically on the first order system in the chapter 3 on the time response. Okay, let's say here in the time domain analysis, the response of any dynamic system is basically given any input is basically respond in the function of time. Okay. The second point here to say it is possible to compute the time response of any system if the nature of any input signal and the mathematical model of the system is very much known. Okay, this slide basically I can summarize that any dynamic system, if you want to analyze the response, actually the response will be in the form of expressed in function of time, meaning that we can basically analyze the behavior of any dynamic system over a period of time, from the starting of any dynamic system to the steady state system. So from the starting time t equal to 0, and from the steady state condition t. So this is basically the response behavior of any dynamic system. And of course, if we want to be able to analyze or to predict the behavior of the system, we need to work with some kind of known input signal. And if we have the system or the control, the dynamic system transfer function, we work with a known input signal, we more or less able to predict the behavior of any control system. Okay, so again, we build the control system. We have the what we call that transfer function of the system that we built from the mathematical model. And then when we have our transfer function, we basically want to test the system using some test signal, some input signal. It says here, point number 2, it is possible to compute the time response of a system if the nature of the input is known. So in this slide, we are going to see the input signal, okay, the test signal that we basically normally we work with. All right. Typically, when you have a control system running, the type or the kind of input signal or the kind of interruption or the kind of I would say the nature of input signal can be categorized into largely in several categories. For example, here we the system that we built can work with some kind of shock signal, sudden change of input. Sometimes the system experience constant velocity and acceleration, or any kind of I would say disturbance that may take any of this behavior. All right. So the point number 2 here, they say that dynamic behavior is judge and compare under application of standard test signal. All right, we have impulse response, we have step, velocity, and acceleration. Another standard signal also important, which is sinusoid. All right, so this is the first test signal that we are going to look at, which is the impulse signal. So you can see the response of the impulse signal only at t equal to 0. Here we have a pulse with a magnitude of A, and the rest of the time after and before the t equal to 0, the amplitude is basically 0, and from this definition we have only amplitude, one pulse, when t equal to 0, and the rest and the remaining of the signal there is nothing. So if A, the amplitude of the pulse, is equal to 1, so we call that unit impulse signal because the amplitude is 1. Okay, that's the impulse. Then we have basically the step signal. For the step signal, the response is something like this. U of t, we have the amplitude of A after t larger or equal to 0, and the amplitude is 0 for t less than 0. So you can see from this graph, before t equal to 0, the output is 0. After t equal to 0, the output is taking constantly A. So if A is equal to 1, the step signal is called unity step signal. All right, so this is impulse. So this is impulse. We observe only one pulse at t equal to 0 in this case. For the step signal, we will observe the change of amplitude, like a step function, right, when t is equal to 0. All right, then we have the ramp signal. The ramp signal imitates constant velocity. Okay, so we have the amplitude of A will correspond with the time for t equal or more than 0. You can see the graph going up. So the amplitude of t is taking the A with the function of t. So as t increase, A will increase in this case because A is multiplied by t here. For example, this is when t is equal to 1, you will have RT is equal to 1A or A1, okay, which is shown in the graph. But when you have t is equal to 0, t is increasing equal to 2, then you have 2A here. Okay, 2 multiplied by A, you will have R of t equal to 2A. So this is where you can see how this thing map, and the graph is basically work that way. Okay, and again, if A is equal to 1, the ramp signal is called unity ramp signal. Another test signal that I want to introduce is parabolic signal. Parabolic signal basically imitate constant acceleration of the input, and this parabolic signal takes the magnitude of AT squared over 2 when t is equal or more than 0. You can see the response and the graph represent some kind of constant acceleration, one of the input signal that you can use to test the stability of or the time response of your control system that you build. All right. Of course, because we have the function of time t here, when the time what they call that increase, you can basically take the t value into the equation, and you will basically get a plot, this kind of plotting. So basically, these are the common test signal that we use in order to find out the characteristic or the time response of any control system. In order to do that, we have to have a transfer function of our control system. All right. So this is because to be able to do this, we have to be working with the Laplace transform with a forward or inverse. So for the impulse signal, basically the Laplace of any impulse signal is basically the magnitude or the amplitude of the signal. If A can be taking any number, because it is just a constant. Can be 2, can be 3, can be 5, can be 10, can be 100, can be 1000. For the step signal, the Laplace transform of unity step signal is the amplitude of the signal. Okay, it can be 1, 2, 3 is a constant over the S. For the ramp function is constant over S square, and for the parabolic signal, the Laplace is 2 times the constant over S cubed. All right. So again, the time response of any dynamic system response to an input is expressed in function of time. Of course, because when we speak about the first order system, this kind of system depend largely on the time that basically run through the system. We want to see how the system behave at t equal to 1, at t equal to 2, at t equal to 3, and so on until the system reach steady state. So for first order system, basically it takes some time for the system to reach steady state from the boot up or from the startup period. All right. For example, here if we have a step response, the system will be the output of the signal or the transient response will be taking something like this. If we give an impulse response, we maybe observe something like this. All right. So the time response of any control system can be divided into two, okay, which we are very much interested in. The first is the transient response. The second is steady state response. Okay. This all right. From this graph, you can see that from 0 to t equal to 16, this is the period where any control system start up, and over the time they will develop the system response, the amplitude or the values, and will increase and will achieve stability or steady state. And then after t bigger than 16 seconds here, the system basically reach steady state condition. All right, so we have two things here. Previously, there is a transient response, this period, boot up period, okay, and steady state response, and when the system reach its final expected target. So as an example, you can take like the window operating system. When you hit the start button, the power button, it will take some time for the system to boot up, to load all the BIOS, to load all the OS, and then when you reach to the window, you are basically reaching at this state. So this is where the system should be, showing a very stable and steady operation. But for this particular stage, basically this is the moment, this is the time where the system takes to prepare itself to the stability state. All right, and of course during this transition time, basically the system is not ready for you to work. All right, transition response basically depends on the system pulse and not the type of the input. It is therefore sufficient to analyze transient response using a step input. So meaning that the transient response of any system basically depending largely on the system pulse. All right, doesn't really matter what kind of input you put in, because the characteristic of the response of the transient response depend only on the pulse of the transfer function of the system. Okay, so for for the first order system, normally they have only one pole, right? You can take, for example, this transfer function Cs over R of S equal to K over Ts plus 1. So in this particular example, in this particular transfer function, K is basically the DC gain, and T basically is the time constant of the system. Okay, the time constant is a measure of how quickly first order system respond to a unit step input. This is particularly for this case. Okay, they say the time constant is a measure of how quickly first order system respond. Okay, so if you have big they call that T, all right. So your time response will be very long. If you have small t, the capital T, so your response will be very quick. Okay, the DC gain of the system is ratio between the input signal and the steady state output value. So DC gain works on the amplitude and basically it's a ratio between input and output of the system because it is just a constant. All right, so the first example, the first order system is given as this equation, G of S is equal to 10 over 3S plus 1. So in this case, DC gain is 10 and time constant is 3 seconds. And for this following system, 3 over S plus 5. Okay, and you can do this kind of conversion where you will have the DC gain is equal to 3 over 5, and of course the DC basically 1 over 5. You can easily pick up the information from a simple transfer function equation and characterize the transient response straight from this equation. So let us see how we basically when we have a transfer function, how do we test our transfer function using in this case impulse response. All right. So on your left here is the impulse response. On your right here, this is your control system. You have your output Cs, input R of S, and this is your transfer function K over Ts plus 1. So this is your impulse response. Okay, so this is your transfer function. So what happens is that because the Laplace transform of your impulse response is equal to 1, basically nothing more or less will be happening. Okay, so when you rearrange the thing, you have this kind of transfer function. After working with the impulse response, and finally you will have something like this, and you take inverse Laplace, you will get back the domain which is C of t, function of time k over t, your time exponential minus t over capital T. Okay, so basically you can draw a simple response or a simple graph from this equation. Exponential, negative exponential, you can basically take any value of what they call that k and t, and you put in the value of t, so you will get basically this kind of graph. So this is how you work with how you test your first order system with the impulse response. The step is more or less like that until you will take the inverse Laplace, and then you can draw the graph, and from the graph you know how the system basically work. Okay, so the second example here is the step response as a test signal to a control system with a transfer function of k equal over Ts plus 1. So when we take the Laplace transform of any step response of this step response equation, you will have 1 over S. So when we basically inject the signal into the system, we will have 1 over S here in the system, Then we we have our control system taking in this behavior, but the statement say we have now to do the inverse Laplace, but before you can do that, you have to break the whole equation using a partial fraction expansion. In this case, all right, example here is all being given. Then after you finish the partial fraction, basically you can take the inverse Laplace, and you will be having something like this. This is more or less the equation. Okay, you can do the detailed calculation yourself, basically. And when you set u of t is equal to 1, basically this is your equation. But when you have your t equal to capital T, this is your equation. So you more or less know this. Okay, and of course, plotting the graph, you can put the t value in the equation, and basically you will get this kind of behavior. And this is the graph that you should get from first order system when you give a disturbance signal in the form of step response. All right. Of course, you can use the equation. You can give more and more values. This is the graph that you're gonna get. All right. This is the time. This is the gain. So when you basically increase the gain, you will see this thing changing. So the time will be changing when the t is equal to 1 second. Basically, the gain is very high. So when the gain is very high, you can see that it takes shorter time to reach stability. Okay, during the first 5 seconds on this blue graph, the system almost reached its stability. But when you lower the gain, okay, when more time to reach stability. For example, here, this is more or less the number of seconds the system take to reach 63% of the whole time response. All right. So again, the same thing I was explaining just now regarding the time and the gain of the control system. Okay, you can basically do it again. So the relationship between step and impulse response, the step response of the first order system is something like this. When you do some kind of differentiation to the step response, you will have something like this. All right. So the step and the impulse response basically is interchangeable terms by differentiation and integration. Okay. So I have here one example. Impulse response of a first order system is given as below. C of t equal to 3 the exponential of negative 0.5 t, and then find out the time constant t. All right, find out the DC gain, okay, and transfer function, and of course the step response. All right, you can try this exercise yourself. Okay, you have the impulse response first order system. The first thing to do is find the constant t. So what you need to do here is something like this. You have to convert this thing to the Laplace, what they call that equation using Laplace transform. Of course, you can find this information from the table. You can straight away convert this time domain equation to the Laplace domain equation, in which now you have 6 over 2s plus 1. You can do the detailed calculation yourself, basically. Okay. Okay, from this equation, you can straight away convert. And then this is your impulse response coming in, right? And basically you can do this. All right. Time constant t. We need to find the time constant t. Okay. So from this equation, you can straight away find t is equal to 2. Okay, and the DC gain is equal to 6. All right, straight from the equation. This is our transfer function. Now we will be working on the step response. For the step response, you have to integrate the impulse response. You will have something like this. And of course, we can. This is basically your step response. Okay. And this is where you put in the step input. All right. This thing they want the step response. When to be able to get the step response, you have to what they call that, integrate. Just not, yeah, here you have to integrate your impulse response. Okay, and from here you have to basically convert, solving the fraction equation, and you will get the impulse response from the system. Okay. Practical determination. Okay, another way to find system function is basically you can analyze from the graph. Previously, what we have seen is just that we draw the graph from transfer function after you inject the system with any kind of test input signal, which is it can be parabolic, can be ramp, can be unit step, can be impulse. In this case, you can practically get the system transfer function by looking at the transition response or the graph. In this case, you have the graph here, which reach 0.72 K for I would say at a state condition. So from this graph, basically here you can measure the time constant. There is the time for to reach 63% of the final value. So you can take 63% from 0.72. Basically, 63% from that 72 is basically taking this value 0.45, and what they call that 0.13 seconds, right? And K is simply the value of the steady state. So this is another way of finding out system control system or dynamic system transfer function just by looking from the graph. Okay. Of course, before this, we have seen we have a transfer function, and we use that to plot plot a graph or to draw a graph by putting the. But in this case, we have only the graph, and from the graph, we try to come up with a transfer function. So because this is what they call that, for the first order system, you can simply say that the K is this one 0.72 over 0.13 second, the T, the capital T, as plus 1 in this case. All right, this is a very basic response for first order system. Okay, of course, you can do the simplification, and you will finally have the whole transfer function of the system given by this graph is just this one. Okay, so I believe that's all for this order system. Thank you very much.